All right, here we go, Titans. First off, somebody asked me the other day what the daughter corn said to the mom corn. Where's popcorn? I actually really do like popcorn. All right, we're going to start with a warm-up today just to get us refreshed with solving by factoring. We're going to start graphing using factored form today, which, as you probably can imagine, has something to do with factoring. So if we factor this, we put our first term in the first box, last term last box, multiply those, get 12x squared. We need to add to a negative 8x, which means our two unknown boxes, in order to multiply to positive 12 and add to negative 8, are going to be negative 6x, negative 2x, which will give us, factors of x minus 6 minus 2. So our factors are x minus 2 and x minus 6. And since we're solving, we'll go ahead and set each factor equal to 0. X minus 2 equals 0. Add 2 to both sides, and x equals positive 2. Same thing, we're going to set x minus 6 equal to 0. Add 6 to both sides, and we get x equals positive 6. So we've talked about those being the solutions, but we've also mentioned that there also are roots or zeros or x-intercepts. So what we've really found by solving by factoring is the x-intercepts of our graph. All right, another example of factoring. This time we don't have a c value, which means we can automatically take out the GCF. And also, if our a is negative, we always remove the negative. So my GCF on this is actually negative 2x, which will leave me with x plus 3, right? Because negative 2x times x is negative 2x squared, and then negative 2x times a positive 3 will get me back to the negative 6x. And so this is going to be the factors, and now we can set each of these factors equal to 0. So I can do negative 2x equals 0, divide by negative 2, and x equals 0, which means one of the x-intercepts of this graph will be 0. And then our second one, subtract 3 on both sides, and x equals negative 3. So 2 solutions also means 2 x-intercepts, and that's what we're going to start talking about. When we graph quadratics, there's 3 main forms of quadratics we can use. Similar to how in IM1 when we did linear equations, you had slope-intercept form, and then you also had standard form. So you had 2 different forms of the equation. With quadratic, we actually have 3 forms that we're going to learn. And the first one is factored form. And so factored form is a times x minus r1 times x minus r2. Well, we've seen a before when we were doing standard form. And this a is the exact same thing as the a from standard form. So when we change this back into standard form, which we'll do later, the a value here will be the same a value we get when we do standard form. The main thing that the a will tell us is whether or not the graph opens up or down, which will also help us to know if it has a minimum or a maximum. The R1 and R2 just mean that this is my first root and this is my second root. Okay, we've talked about roots a little bit. We said roots are really just the solutions. So this is saying that whatever number is here is one of the solutions, or x-intercepts, and whatever number is here is the other solution, or x-intercept, or we call roots. So let's go ahead and explore this a little bit. We're going to open up Desmos. Well, I'm going to open up Desmos. And I typed in the factored form right here. And then I made a slider for the A, the R1, and the R2. So the first thing we want to observe is what happens when we change our A value. Right now I have it set for positive 1 because that's usually what we see. And if it's an A value of positive 1, notice our graph is opening up. If we make the A value larger than 1, you'll notice that the graph starts to get skinnier and skinnier. When it gets skinnier like that, we call it a stretch. We're going to talk more about stretching graphs later. But as we make the A value smaller, the graph starts to get wider and wider and wider, which we call a compression. So the graph gets compressed as the a value gets closer and closer to 0. But what do you think is going to happen when I make the a value negative? Well, if we make the a negative, our whole graph flips from concave up to concave down. So as I go in the negatives, the more negative I get, the further from 0, the skinnier or more stretched it becomes. And then as I go back towards 0, it's going to compress or get wider. All right, especially when I get into those numbers between 0 and 1, it really starts to get much wider. And then if I go to 0, it actually becomes a straight line, because if our a is 0, this will no longer be a quadratic equation. Don't worry too much about that. The main point I want you to see is that if your a value is positive, your graph is up. If your a value is negative, your graph opens down. All right, I'm going to set this back to 1. The next thing I want to look at is the R1 and the R2. We said that the R1 and R2 represent the solutions or the x-intercepts. So if I change this root to 5, that means I should have an x-intercept at 5. And if I look over here, boom, I have an x-intercept at 5, 0. If I change the other one to, let's say, -2, now I have an x-intercept at -2. So if my roots are 5 and -2, I have an intercept at -2 and +5. The thing that you have to get a little bit used to, though, is that in the formula it says x minus the root. So if we were to write this equation for this particular graph right here, it would be f of x. Well, I guess it doesn't want me to write on it. Anyway, it would be f of x, and then for the +5, when we plug in 5, it's going to say x minus the +5. So x minus 5 actually gives us a solution of +5. Which means if we're going to plug in a -2, a negative is going to turn into a positive. So this one would actually say x plus 2, which would mean we get a root of -2. Similar to how when we solve by factoring. All right, just a little intro there to get us going. So again, the key points: if a is positive, we know the graph will open up. Okay, and again, if the graph opens up, do we have a minimum or a maximum? Well, if it's opening up, we change direction at the bottom, which means we will have a minimum. So anytime we have a positive a value, the graph will be concave up and have a minimum. However, if a is negative, we know that that means the graph will open down. So it'll look something like this, concave down. And if it's concave down, we know that it'll have a high point at the top, which will be called a maximum. And then the R1 and the R2, we said those are going to be our roots, and we're going to get lots of practice with that. Okay, so the two problems that we started with in the warm-up, when we factored, we essentially, halfway through the problem, we put them into factored form. So we had x minus 2 times x minus 6 equals 0. Well, if that equals 0, I can rewrite this as f of x equals x minus 2 times x minus 6. That is actually the factored form of that problem that we did. The a value is always in front, and if we don't see anything there, what is our a value? Our a value is a +1. If that a value is a +1, what do we know? We know that the graph will open up, and we also know that we will have a minimum. As far as the R1 and R2, we know the formula is x minus the root. So this is x minus 2, which means 2 is one of our roots. So 2, 0 is a root, or I'm going to say it's an x-intercept, because that's really what we use the roots for. And then this one is x minus the root, so the root is +6. So we know that 6, 0 is the other x-intercept. So again, if it's in factored form, long story short, whatever number is here, right, it says -2, it's the opposite. So the root is actually +2. This root is +6. The other example, if we rewrite it in factored form, we had -2x, and then x plus 3. And the reason I put this parentheses right here is just to show that if it's just a single x, that means it's really the same as x minus 0. So we do get 2 roots from this because there are 2 factors with x's. The a value, first off, is -2. And if our a is negative, we know that the graph will open down. So just make sure we're clear. Down. And we have a max. So again, if our a value is negative, the graph will open down, we have a maximum. The R1 and R2 for this are going to be 0 and -3. So we know that the intercepts, the x-intercepts, are going to be 0 and -3. Those are going to be our 2x intercepts. So the roots give us our x-intercepts. All right, so one thing that you might be thinking, or you might at some point wonder, is this is supposedly the factored form of a quadratic equation, but I thought quadratic equations always had to have x squared, right? If it's squared, you get the parabola. So where is our x squared in this function? Well, how do I multiply those together, right? If I multiply those together using the box, or the area model, we end up getting x squared, so boom, there it is, minus 2x minus 6x plus 12, and if we rewrite this out, it's x squared minus 8x plus 12. So that it is a quadratic equation. When it's in factored form, it might not look like it's quadratic, but once we multiply those out, we do in fact get the x squared. So that is why we are getting parabolas. Okay, looking at the graphs of quadratics, this is the standard form. We'll talk more about standard form in a future lesson. But the factored form of this is x minus 2 times x minus 6. Well, if it's in factored form, we know that the roots, or the x-intercepts, are going to be the opposite of 2, so positive 2. And then the opposite of -6, so positive 6. And if we look at the graph, we can confirm, yep, there's one x-intercept of positive 2, the other x-intercept of positive 6. The other thing we know from factored form and standard form is since our a value is 1, that means the graph's going to open up, right? So it's opening upward. Because it is opening up, this point down here, which is our vertex, right? Our vertex is going to be a minimum. And those are the main things we're looking at for now, right? We talked yesterday about domain and range, and I just, let's go ahead and do that real quick. Domain, always all real numbers, or sometimes we use a symbol that looks like that. The range, however, is all of the y values, which are y values, the lowest we go is -4, but other than that, every y value is above -4. So our range is y is greater than or equal to -4. And then the graph is increasing from here over. So our interval of increase would be 4 to infinity, but the interval of decrease would be -infinity to +4. So just a little refresher on those things as well. Okay, this graph is concave down, all right, opening down. How did we know it was going to open down? That's right, we look at our a value is negative. If there's just a negative there, it means our a is -1. But anytime our a value is negative, the graph will open down, which means our vertex up here is a maximum. right? So the key points, negative, opens down. If it opens down, the vertex is a max. And then our factored form gives us our two roots as well, which we know it's going to be the opposite of whatever number is in here. So the opposite of positive 4 is going to be negative 4. That's going to be one x-intercept. And then our other x-intercept is going to be the opposite of negative 2. So it is going to be positive 2. So again, when it's in factored form, we can look at it and quickly know that opposite of this, negative 4, and opposite of this, positive 2. Those will be our two x-intercepts. There's our intercept at positive 2, 0, and our other one at negative 4, 0. All right, determine the x-intercepts of each quadratic function from its factored form. Then determine if each function will have a maximum or minimum. These are actually very simple problems. If we look at our factors, if this is x minus 2, we know that it's going to be the opposite. So my x-intercept, or my x-intercepts, the first one will be the opposite of negative 2, so it would be positive 2. And my second one will be the opposite of negative 8, which is positive 8. You can also think of it as like when we were solving, right? If I set x minus 2 equal to 0, and I solved it by adding 2 to both sides, I would get a solution of positive 2. That's why our x-intercept is positive 2. Same thing, if I do x minus 8 equals 0, I would add 8 to both sides, and I get x equals positive 8, right? That was our solution. So that is also why our intercept is positive 8. Okay, second part of the question is, does it have a maximum or minimum? Well, our a value is positive, so a is a positive 1, which means our graph will open up. And if our graph opens up, do we have a minimum or a maximum? Since it's down there, we have a minimum. All right, x-intercepts on this next one. It's going to be the opposite of positive 1. So we get negative 1, 0. And then the opposite of negative 6. So positive 6, 0. Our a value is 1. And because that's a positive, our graph will open up. And because our graph opens up, that means our vertex is a minimum. Next example, we have an a value of 3 this time. So I'm actually going to skip ahead to that. Our a is 3, but it's still a positive, right? So if it's positive, it's going to open up. The only thing the 3 does is it stretches our graph. It's going to make it skinnier. But we still have concave up. Therefore, we still have a minimum. And then for our x-intercepts, we have the opposite of 4, so negative 4. And then we have the opposite of negative 2, so positive 2. I'm going to adjust one thing for this last side because I want to have one that's actually a maximum. So if I want to make this whole function become a graph that would have a maximum, what do I need to do? That's right, I need to take my a value and make it negative. So if I have a negative a value, that means the graph will open down. The fact that it's a decimal close to 0 just means it's going to be compressed, it's going to be wider, but it's still going to point downward. And if it opens down, that means we have a max. But whether this is positive or negative doesn't change the x-intercepts. Our x-intercepts are still going to be the opposite of what is in the parentheses. So if we have negative 1, that means our intercept is positive 1. And if we have negative 12, it means our other intercept is positive 12. Hopefully you're starting to get the hang of this. It's not too bad. All right, determine the x-intercepts for each function using your graphing calculator. Then write the function in factored form. So I obviously pre-planned this so I didn't have to go type this in a graphing calculator. You would use Desmos.com. Hopefully you've used that before. But when I graph it, I get intercepts of 1, 0 and 7, 0. So I know if I'm going to write this in factored form, in order to get an intercept of 1, I need my parentheses to say the opposite of 1. So it needs to say x minus 1. And then to get positive 7, I need my other parentheses to have the opposite of positive 7. So it needs to say x minus 7. And then of course I need to find the a value, which the a value is just a positive 1. So I could put a 1 there, but usually we don't. I'm just going to leave that blank. And this is our factored form for this graph. The second one, I know my intercepts are negative 3. So my parentheses need to be x plus 3. And then my second intercept is positive 8. So it needs to be x minus 8. But this time we do have an a value other than 1. So if I look at the standard form, I know that the a is 2. And the a in factored form is still the same a. So if this a is 2, then our factored form will also have an a value of 2. Determine another point on each parabola. Okay, I like these problems because it makes you think a little bit. We have to think about the symmetry aspect of a parabola. And so if we know the axis of symmetry is x equals 3, but then we have a point on the parabola at 1, 4, could we find another point on this parabola? Well, yeah, definitely. Because we know that the distance from this point to the axis of symmetry will be the same distance as the axis of symmetry to another point. To make it make a little more sense, I'm going to show you on a graph, and then I think you can get to the point where you can do these problems without a graph. So the first thing I'm going to do is my axis of symmetry is at x equals 3. That's a vertical line through 3. We know that there's a point on the parabola at 1, 4. And if this is an axis of symmetry, that means we have like mirror image, right? So if we have a point that is 2 spots away from the axis of symmetry, don't we have to have another point that is 2 spots this way? So we would have to have a point right there. That way it's symmetric. So if we have a point at 1, 4, we have to also have a point at 5, 4. What I'm hoping that you notice is that my x values of these 2 points are 1 and 5. And how are those related to the axis of symmetry of 3? Well, 3 is exactly halfway between 1 and 5. So even if I didn't have the graph, I would know, oh, 1 is 2 spots away from 3. And then the other number that's 2 spots away from 3 would be 5, right? So my new x value has to be 5. And then the y values stay the same because we're just going straight across. We're not moving up or down at all. And so we'll always have a symmetric point where the y values remain the same. Another type of problem we could ask you similar to this would be giving you the vertex. So the vertex on this one is negative 1, 6. And then telling you that there's another point at positive 2, 3. And asking you to come up with another point on this parabola. Well, if our vertex is negative 1, 6, what is our axis of symmetry? Well, we know our axis of symmetry has to go straight through that vertex. So our axis of symmetry is just x equals the x-coordinate of the vertex. X equals negative 1. Now, using kind of this idea over here, how far is 2 from negative 1? Well, it's 3 spots away. What other x value would be 3 spots away from negative 1? Well, if I add 3, I go to 2, and I already did that one. So my other option is to subtract 3, which will take me to negative 4. And then since we're looking at points that are across from each other, we are not going to change this at all. And I get negative 4, 3. Now I can prove it using the graph, and hopefully visually this will help you see why this works. We put our axis of symmetry at negative 1. I can count that this is 1, 2, 3 spots away from the axis of symmetry, which means I need to have a point 1, 2, 3 spots away on the other side. And so I have to have a point on my parabola that'll be right there. And this is the ordered pair, negative 4, positive 3. Negative 4, positive 3. So the parabola would look something like that. So again, parabolas will always have symmetry. The line that divides it into two equal halves is called the axis of symmetry. Which, what do you know? Axis of symmetry. So if we are in factored form, we can find the axis of symmetry very quickly if we know the two roots, because we know the axis of symmetry will always be halfway in between. So if we know that the factored form is x minus 5 times x minus 11, we know that our roots will be positive 5 and positive 11, right? Our x-intercepts would be 5, 0 and 11, 0. Well, what is halfway in between 5 and 11? So you could probably do this in your head, but if you want a formula, you just add the roots together and divide by 2. So I can do 5 plus 11 divided by 2, which is 16 divided by 2, which is 8. So if my roots are 5 and 11, my axis of symmetry is x equals 8. The a value is not relevant in this case because the a value is just telling us if the graph opens up or down. We just need to find the roots. So again, the roots on this one are -1, right? Opposite of 1. And then the opposite of -5 is positive 5. So what's halfway between -1 and positive 5? Well, you can probably do that in your head. Axis of symmetry is x equals 2. If you're not a big fan of doing math in your head, that's fine. We go back to our formula, right? X equals R1 plus R2, so -1 plus 5, and then divide by 2. So that's positive 4 divided by 2, which is 2. So again, our axis of symmetry will always be in between the roots. Similar to that, even though these points aren't roots, they are symmetric points. So we basically did the same thing here. If we add the 1 and the 5, which is 6, and cut it in half to get 3, that gives us the axis of symmetry. All right, we're just going to go through a couple of final examples, make sure we're doing okay with our vocabulary. This graph shown, here's the standard form, but if we put it into factored form, I can do that quickly by identifying the x-intercepts. X-intercepts are 0 and 2. So 0, 0, and 2, 0, which means to put it in factored form, I'd have x minus 0 and then x minus 2. But then we also have to make sure to put the a value out front, and our a value is -2. And then we would simplify this because what is x minus 0? It's just x, right? So I would rewrite this as f of x equals -2 and then x parentheses x minus 2. So putting it in factored form. But as we go through this graph, the graph goes left and right forever. So domain is all real numbers. The range is all of the possible y values. The highest this graph goes is right here, which is a y value of 2. So our graph is always less than or equal to that highest point of 2. Excuse me, put that in the wrong spot. Let's move that up. There we go, that's our range. The y-intercept, we just look to see where the graph crosses the y-axis, which was 0. Our axis of symmetry, we go to our vertex and we draw a vertical line. And if it's hard to see, this is actually a 1 right there. So we're going through 1. So our axis of symmetry is x equals 1. Our vertex, we know the x is always the same as the axis of symmetry. And then if I look at this point, this is the ordered pair 1, 2. So my vertex is